So in this question, it's question 2 from 2019 for the Pure 1. And we've got a function y equals x cubed sine kx. And what we want to do is show that the fifth derivative of this function, d5y by dx to the power of 5, equals this thing. And it's a really long and complicated expression. The way we're going to get there in further Pure 1 is by using Leibniz's differentiation rule. And just to remind us what that actually is, let's work it out from scratch, or derive it from scratch. We have to start off then with y is a function that can be written like this. So y can be written as uv, where u and v are both functions of x on their own. So this looks like a product, the kind of thing we could use product rule for differentiation. The first derivative then, if we have y equals uv, we know that y dash, or the first derivative, will be u dash v plus uv dash. Right, that's just the product rule. And now this is where we're going to start thinking a bit more deeply as we continue to differentiate this. Let's differentiate y again then to get y dash dash, or the second derivative of y. And what we need to do here is use the product rule again, but we're going to start seeing some things interact in the middle. So using the product rule on this, first of all, on u dash v, we'll get u dash dash v plus u dash v dash. We differentiated u and u dash and left v the same for u dash dash v, and we differentiated v to get v dash and we kept the u dash there. We also have two terms coming from here though. So we will get u dash v dash plus u v dash dash. And actually we can combine some of these together and make it look a bit nicer. We get u dash dash v plus 2 u dash v dash plus u v dash dash. That's really nice. It makes a nice symmetrical pattern. We're going to try one more and then we'll see if we can think about this more generally. So let's try the third derivative. That's y dash dash dash. And when we differentiate this thing first with product rule every single time, we'll get u, the third derivative of u dash 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 v. Here though we'll have u dash dash and then a v dash, because this v needs to be differentiated as well. So u dash dash v dash. Now when we differentiate this, the middle term, first we'll get 2u dash dash v. That comes from us differentiating the u dash to u dash dash. So that should be v dash. And then when we differentiate the v dash, we'll get 2u dash v dash dash. And now we do the last term, and two terms will come out of this. We'll get u dash v dash dash, and the other one will be u v triple dash. Okay, this looks quite complicated, but actually we can see some nice simplifications. That first term we can't do anything with. It's the third derivative of u and just v on its own. Well, this one though, we've got u second derivative, v first derivative, and that's the same thing we've got here. We've got one of them and then two of them, so we've got 3 in total. So we've got 3u dash dash v dash. Well, here we've got something similar as well. The first derivative of u and the second derivative of v, and we've got 2 of them and another one. So we've also got 3 here. 3u dash v dash dash. And then we've got our last term, which is uv triple dash. Okay, once again we've got this nice symmetrical pattern, and let's take a step back here and just think what we've got. We had uv, then we had one u dash v and one uv dash. We're looking at the coefficients in front of these numbers. Then we had 1, 2, 1. Now we've got 1, 3, 3, 1. If we think of the pattern that these are making as we go down the derivatives of y, well, we had the first row would be 1, and in the second row the coefficients would be 1 and 1. The third row, the coefficients would be 1, 2 and 1. And the fourth row, that's the third derivative of y, we would have 1, 3, 3, 1. So let's make this its own box, 3, 3 and 1. What we can see here is that these coefficients, 1, 3, 3, 1, on this row, they are the coefficients that you'd find in Pascal's triangle. And it's exactly the same as if we were to expand a binomial. We get these same numbers. These are the binomial coefficients. So thinking more generally, we could think, well, the fourth derivative of y is going to have these coefficients. 1, we add the 2 that we see above it, so 4, 6 from 3 and 3, 4 and 1, and so on. We know how the binomial coefficients look. Let's try and think of a more general way then of writing the nth derivative of y. So we could write dny by dx n. That's the nth derivative of that function y. And what we have for this nth derivative, if it's a sum of terms. So we need to write it as a sigma sum. And what's really important here for us to realise is that for the third derivative, for example, if you look at each term, we start off with the third derivative of u and the 0th derivative of v. And then we have the second and the first derivatives, then the first and the second, and then the 0th and the third. The derivatives, they always add up to 3 if we're looking at the order of them. So what we've got here then is we've got a sum from 0 to n. So we like to say r equals 0 up to r equals n. For the third derivative, this would be up to 3. And what we've got is we've got u to the rth derivative. We're taking the rth derivative of u. So that would vary from 0, 1, 2 to 3 in this case. And when we have the rth derivative of u, well, we have v and we have the n minus rth derivative of v. Because if u was 0, v would be 3. These two have to add up in total to our n. Well, we're missing one more thing from our sum, and that's the coefficients that we find. The coefficients we need to add in, and we write them like this, like a binomial coefficient, is n choose r. So we could think, for example, in our third derivative, if it was n choose r, well 3, and here this would be u to the r, would be 3. 3 choose 3, that just gives us 1. There's only one way of choosing 3 objects from 3 total objects. We're happy then that this is our formula for Leibniz's differentiation rule. So let's close this area off. Now what we can actually do then is think, how can we prove this result for y equals x cubed sine kx using Leibniz's differentiation rule? Let's have a look. What we need to do first of all is choose u and v here, don't we? And it seems pretty natural that we choose u to be x cubed and v to be sine kx. So let's write that down. So u equals x cubed, v equals sine kx. We make that a little bit nicer, there we go. U is x cubed and v is sine kx. And what we'd like then, for the fifth derivative, because we want d5y by dx to the power of 5, we need to think about the derivatives up to the fifth one for u and v. So let's work through with u first. The first derivative will be 3x squared. This is nice and easy for this one. The second derivative will be 6x. The third derivative will be 6. The fourth derivative, I'm going to write it like this, using this same kind of notation. U and the power will be brackets 4. Not to be confused with the fourth power of u, this is the fourth derivative. This will be 0, because when we differentiate a constant, we just get 0. And then nicely for us, any higher order derivative of u is still going to be 0. Once we get to that 0, we're stuck. We now want to do a similar thing with v. So the first derivative of v of sine kx is going to be k cosine kx. Now we differentiate again. The second derivative is going to be minus k squared sine kx. And we know that when we're differentiating sine or cos, another power of k, or that function in the brackets, is just going to pop out each time. So the third derivative, v, 1, 2, 3, will be minus k cubed cosine kx. v4 will actually, 1, 2, 3, 4, we could have written it like that as a 4. We'll see minus cos differentiates to sine, so we'll have k to the power of 4 sine kx. And lastly, our fifth one, let's do it like this, v5 will be k to the power of 5 cosine kx. Okay, so now we need to think about actually putting these into Leibniz's differentiation rule. Let's try it then. So we can write y to the power of 5, y like this, the fifth derivative, not the power of 5. And we need to say, first of all, we think about this formula when r equals 0. So we need 5 choose 0. Let's write it like this, 5 choose 0. This will be u0. So just, we haven't even differentiated u, we've just got this, we've got x cubed, and we want v to the 5 minus 0th derivative. So that's just the fifth derivative of v. So this is k to the power of 5 cosine kx. That's the first term in this sum. Well, now let's think about the second term. So the second term is when r equals 1. And putting r equals 1 into here, we're going to get 5 choose 1. The first derivative of u is going to be 3x squared. And we now want the fourth derivative of v. So that's k to the power of 4 sine kx. k4 sine kx. Yep, agree. Now continuing on then, we want 5, so plus 5 choose 2. We're now looking at evaluating this term when r equals 2. So we want the second derivative of u. And what's nice here is you can see we started out here, then we went to the first and fourth, now we're going to the second and third. We keep switching along, we're going down this row, up this row. So 5 choose 2, well, the second derivative of u, so that's 6x. And the third derivative of v is minus k cubed cos kx. So let's put k cubed cos kx. And actually, instead of having a plus at the front, let's make that minus. Because we know we need to switch it to a minus. I'll move out of the way now. We've got 5 choose 2. We now want the third when r equals 3. So plus 5 choose 3. And 5 choose 3. We want u, the third derivative, so it's just 6 in here. And we want the second derivative then. So we want minus k squared sine kx in this one. So let's add k squared sine kx. And because it was a minus, again, we need to get rid of this plus sign here and make sure it's a minus. Okay, just 2 more terms to worry about then. So now we want the 5 choose 4 term. And 5 choose 4, that means we're choosing r to be 4, so we want the fourth derivative of u. Luckily for us, this is 0. So actually, this is just a 0. And then if we're smart, we realise that means the next term, the 5 choose 5 term, must also be 0 as well. So we don't need to worry about those last 2 terms. They are definitely just 0. At this point, I'm going to have to clean the board and then we'll start again. Okay, we are back and I've cleared some space on the board. So if you remember, we were here, we've just plugged all of these into Leibniz's differentiation formula, and now we actually need to evaluate this. So let's start again over here. We've got the fifth derivative of y. So let's write this up here. y 5 in brackets, the fifth derivative of y. And now we need to think about what some of these terms mean. Well, 5 choose 0, first of all, is just 1. There's only one way of choosing 0 objects, no matter how many we've got. So we've got x cubed k to the power of 5 cos kx. And if we're here, we can be a bit smarter as well, because we can see we're going to get a bunch of terms which all have cos kx involved. There should be a kx here as well, which I forgot to put in there earlier. So cos kx, let's just write this over here. And then we need to think of some terms that are going to go in there. We can do the same thing. We can see in our answer we need to think about some sine kx's. So underneath, I'm going to write sine kx. And again, we can think about some terms which will go in here. Let's make this a plus as well. Alright then, think of our first cos kx term. 5 choose 0 is 1, and then we've got x cubed k to the power of 5. So we can just write in there x cubed k to the power of 5. While we're at it then, let's just look at our next cos kx term. And the only other one we've got is this one. 5 choose 2, 6x k cubed cos kx. Well, 5 choose 2 is 10. And we could prove that if we wanted to, because it's 5 factorial over 2 factorial, 3 factorial. But we've got 10 times kx, so 10 times 6x k cubed. So if we put that in, that gives us 60x k cubed. That's our cos kx terms done. Let's have a look at our sine kx terms. And nicely, actually, the coses have both lined up and the sines have both lined up. So we can see for our sine kx terms, we've got 5 choose 1, which is 5 times 3x squared k to the power of 4. So we've got 15x squared k to the power of 4. Let's write that in. 15x squared k to the power of 4. In our other sine term, we've got minus, and by the way, this should have been a minus earlier as well. For our 60x k cubed, this should be a minus here for the cos kx. Those are the kind of mistakes that are going to catch me out. Then we look at our other sine term. We've got 5 choose 3, and because the binomial coefficients are symmetrical, 5 choose 3 and 5 choose 2 must be the same. So we know this is also 10. 10 times 6 gives us 60. So we've got minus 60k squared. So minus 60k squared. What gives us some faith as well that we're right at the moment is if we look at all of these numbers, we seem to have some kind of symmetry going on. You can see each time that we multiply this x cubed, we differentiate the x cubed, we multiply another power out the front. This looks pretty good for now. What we'd like to do then, and we can forget about these two terms as well because they're both 0. What we'd like to do is try and make this look like what they want in the answer. And we can see at the moment, they'd like us to take a k cubed x out of the cos kx term. So let's write this below. So y fifth derivative. We should have k squared x squared plus a. So let's put this in brackets. And when we take out our k cubed x, which we can definitely do from both of these, k cubed x cos kx. Let's think about what we have left. If we take out k cubed x from this, we're left with x squared k squared. So x squared k squared. And that's good because that's what we wanted in here. But then when we take out k cubed x from this term, we're just left with minus 60. That works just fine then, doesn't it? That's our first half of our answer done. Now if we think about the second part of our answer, we want b lots of k squared x squared plus c k squared sine kx. Well, if we look at the moment, we've got our sine kx for sure, that's fine. So sine kx. We already took that factor out. We'd also like to take out k squared, and this looks fine because we've got k to the power of 4 and k squared in our two terms. So we can definitely take out k squared. Well, now in these brackets then, let's think about what we've got. We've got 15x squared k to the power of 4 minus 60k squared. We can definitely take out a factor of 15 from both of these. So let's take out 15. And remember, this needs to be a plus in front. And then when we take out our k squared, well, we've got nothing left to take away from the 60, but we've still got an x squared k squared. That's exactly what they wanted here as well. So x squared k squared, and we should have minus 4, because 50 times minus 4 will give us our minus 60. So this then is our answer. We should have x squared k squared minus 60, brackets, k cubed x cos kx, plus 15, brackets, x squared k squared minus 4, close brackets, k squared sine kx. That's what we're looking for in our answer, and we are done. Let's give that a nice underline. Fantastic.